In the constellation Aquila, 2,600 light-years from Earth, something extraordinary hides in plain sight. Not a star, not a planet, but a gravitational monster 33 times more massive than our Sun. This is Gaia BH3, and its discovery challenges everything we thought we knew about the invisible population lurking in our galaxy. The data came from an unlikely source. ESA's Gaia spacecraft, designed to map stellar positions with unprecedented precision, detected something that shouldn't exist according to conventional models. A star in Aquila was wobbling. Not the gentle dance of a binary system, but the violent gravitational yanking of something massive and dark. Dr. Pasquale Panuzzo of the Paris Observatory first noticed the anomaly buried in preliminary data that wouldn't be released to the public until 2025. No one was expecting to find a high-mass black hole lurking nearby, undetected so far. Panuzzo would later say, "This is the kind of discovery you make once in your research life." But here's what the initial press releases didn't emphasize. Gaia BH3 represents more than just a record-breaking discovery. It's the first concrete evidence that massive stellar black holes exist in significant numbers throughout our galaxy, hidden from conventional detection methods. The wobbling star in Aquila offered clues that extend far beyond a single system. When astronomers analyzed the metallicity of the companion star, they found it contained 100 times fewer heavy elements than our Sun. This wasn't coincidence. It was evidence of a formation mechanism that theoretical models had predicted but never observed. Low metallicity stars lose less mass during their lifetimes, retaining more material to collapse into massive black holes when they die. If Gaia BH3 formed this way, it suggests that the early universe, dominated by metal-poor stars, produced far more massive black holes than we've detected. The implications ripple outward like gravitational waves. George Seabrook from University College London's Mullard Space Science Laboratory put it starkly. Finding Gaia BH3 is like the moment in the Matrix where Neo starts to see the Matrix. In our case, the Matrix is our galaxy's population of dormant stellar black holes, which were hidden from us before Gaia detected them. Hidden. That word carries weight when discussing cosmic objects that fundamentally alter the gravitational landscape around them. Current estimates suggest our galaxy harbors between 10 million and 1 billion stellar black holes. Yet, before Gaia's systematic survey, astronomers had confirmed fewer than 50. The detection method reveals why we've missed so many. Active black holes announce themselves through X-ray emissions as they devour nearby matter. But dormant black holes like Gaia BH3 remain invisible unless they gravitationally influence a companion star detectable by precision astrometry. Gaia's unique capabilities changed the game. By measuring stellar positions to microarcsecond precision over multiple years, the spacecraft can detect orbital wobbles caused by invisible companions. The technique works even when black holes are separated from their companions by distances comparable to our outer solar system. What emerged from the Gaia BH3 analysis wasn't just confirmation of a single massive black hole. It was validation of a detection method capable of uncovering thousands more. The full Gaia Data Release 4, expected in late 2025, will likely reveal dozens of similar systems. But the discovery raised uncomfortable questions about cosmic neighborhood safety. If massive black holes exist in numbers we never suspected, how accurately do we understand gravitational threats to Earth? How many invisible giants wander through the galaxy undetected? Preliminary orbital analysis of Gaia BH3 revealed another surprise. The system's trajectory suggests it originated not in the Milky Way's disk, but in a disrupted satellite galaxy called ED2. This finding implies that galaxy mergers throughout cosmic history have scattered massive black holes across previously unexpected regions of space. The companion star's composition tells a story of ancient catastrophe. Its chemical signature shows no contamination from the supernova explosion that created the black hole, suggesting the star was captured later through dynamical interactions. This formation scenario opens possibilities for black hole systems in regions where stellar evolution alone couldn't explain their presence. As news of Gaia BH3 spread through the astronomical community, researchers began re-examining assumptions about galactic structure and stellar evolution. If 33 solar mass black holes could form from single stars, what did this mean for gravitational wave predictions? What other surprises lurked in the Gaia dataset? The European Southern Observatory's Very Large Telescope confirmed the mass measurement through ground-based spectroscopy, eliminating alternative explanations. With its 11.5-year orbital period and well-determined parameters, Gaia BH3 became the most precisely characterized massive stellar black hole in our galaxy. Yet beneath the scientific celebration, a more sobering reality emerged. Gaia BH3 sits just 2,600 light-years away, making it the second closest known black hole to Earth. At cosmic scales, this represents our immediate neighborhood. The proximity forces a recalculation of local threat assessments. While 2,600 light-years provides comfortable safety margins by any reasonable standard, the discovery pattern suggests that closer black holes remain undetected. Statistical analysis of Gaia's detection efficiency implies that isolated black holes could exist within a few hundred light-years of our solar system. More unsettling is what Gaia BH3 represents about the galactic population as a whole. If one massive black hole exists within relatively close range, how many more massive examples lurk at greater distances? How many failed detections resulted from orbital orientations that don't produce detectable wobbles? The answer may be emerging from gravitational wave observations. LIGO and Virgo detectors have recorded mergers involving black holes with masses similar to Gaia BH3, suggesting that such objects exist throughout the universe. The question becomes, how many reside in our own galactic neighborhood? Researchers began cross-referencing Gaia's preliminary data with other astronomical surveys, searching for additional candidates. Early results suggest that Gaia BH3 represents the tip of an iceberg. Multiple stellar systems show similar wobbling patterns, indicating the presence of massive invisible companions. The discovery timeline itself raises questions about scientific disclosure. Gaia BH3 was identified in preliminary data that won't be publicly released for another year. The decision to announce the discovery early suggests recognition of its fundamental importance, but it also highlights how much potentially significant data remains classified within space agencies. This pattern of selective disclosure extends beyond academic publications. Space agencies maintain careful control over information that could impact public perception of cosmic safety. While no evidence suggests immediate threats from black holes, The agencies recognize that dramatic discoveries require measured communication strategies. The Gaia mission itself exemplifies this approach. Designed as a stellar census, it has evolved into humanity's most comprehensive survey of galactic structure. Yet its most significant discoveries often emerge from data that remains restricted for years after collection. Gaia BH3 forces a confrontation with these information asymmetries. If massive black holes exist in numbers that challenge current models, shouldn't this information be shared with the global scientific community immediately? How many other discoveries await release in classified datasets? The broader implications extend to planetary defense and space situational awareness. Current threat assessment models focus on asteroids, comets, and solar activity. But if our galactic neighborhood contains more massive objects than previously recognized, these models may require fundamental revision. As we prepare to explore the hidden dimensions of this discovery, one thing becomes clear. Gaia BH3 isn't just a new entry in astronomical catalogs. It's evidence that our understanding of cosmic threats has been incomplete. The invisible monsters that populate our galaxy, the mathematics are staggering. Astronomical models predict that our Milky Way galaxy contains between 10 million and 1 billion stellar black holes. Yet, until recently, fewer than 50 had been confirmed. Gaia BH3's discovery illuminates a vast invisible population that challenges fundamental assumptions about galactic structure and cosmic safety. Dr. Kailash Sahu from the Space Telescope Science Institute spent 6 years using the Hubble Space Telescope to identify a single isolated black hole through gravitational microlensing. The painstaking process required monitoring millions of stars for the telltale brightening that occurs when a massive object passes between Earth and a background star. The result? Confirmation of one wandering black hole, approximately 5,200 light-years away, weighing 7 times the mass of our Sun. Sahu's discovery validated theoretical predictions about isolated black holes drifting through the galaxy after receiving kicks from asymmetric supernova explosions. But Sahu's technique, while groundbreaking, can only detect black holes that happen to align perfectly with background stars as seen from Earth. Statistical analysis suggests that for every microlensing event detected, hundreds of black holes pass through the galaxy unobserved. Gaia's astrometric approach offers broader detection capabilities. By measuring stellar wobbles over multiple years, the spacecraft can identify black holes in binary systems regardless of their orientation relative to Earth. This method doesn't require perfect alignment, dramatically expanding the detectable population. The preliminary results from Gaia Data Release 4 suggest that dormant black holes may be orders of magnitude more common than active ones. Unlike their X-ray emitting cousins, these invisible giants betray their presence only through gravitational influence on nearby stars. This discovery pattern has profound implications for galactic archaeology. If massive black holes like Gaia BH3 formed preferentially from metal-poor stars in the early universe, they serve as fossil records of ancient stellar populations. Their distribution throughout the galaxy maps the history of star formation and galactic evolution. But the archaeological perspective raises disturbing questions about population dynamics. Computer simulations suggest that galaxy mergers throughout cosmic history have scattered black holes across previously unexpected regions of space. Some may follow highly eccentric orbits that bring them through the galactic disk at unpredictable intervals. The Large Magellanic Cloud, our galaxy's largest satellite, appears to harbor its own supermassive black hole based on the trajectories of hypervelocity stars ejected into intergalactic space. This finding implies that black hole populations extend beyond the main galactic disk into the surrounding halo and satellite systems. Recent analysis of Gaia BH3's orbital characteristics confirms its association with the disrupted ED2 stellar stream, remnants of a satellite galaxy that merged with the Milky Way billions of years ago. This connection suggests that galaxy mergers have distributed massive black holes throughout regions where they wouldn't naturally form. The implications for space safety assessments are significant. Current models of galactic structure assume that most massive objects follow predictable orbits within the galactic disk. But if merger events have scattered black holes throughout the halo, some may follow highly eccentric paths that periodically intersect with our solar neighborhood. NASA's estimates suggest that approximately 100 million black holes roam among the stars in our galaxy. This number, derived from stellar evolution models and supernova rates, has remained largely theoretical due to detection limitations. Gaia's systematic survey promises to provide the first observational census of this hidden population. The detection efficiency analysis reveals sobering statistics. Gaia can identify black holes in binary systems only when their orbital planes are oriented to produce detectable stellar wobbles. Systems viewed face-on or edge-on may escape detection entirely, suggesting that current discoveries represent a small fraction of the total population. Moreover, Gaia's sensitivity depends on the orbital period and separation of binary components. Wide binaries with periods longer than the mission lifetime may produce signals too subtle for detection. Closer binaries may have undergone mass transfer that altered their observable characteristics. These selection effects compound the challenge of population estimates. If Gaia BH3, with its 11.5-year orbital period, barely appears in the preliminary data, how many similar systems remain below the detection threshold? How many isolated black holes wander through the galaxy without stellar companions to reveal their presence? The gravitational wave perspective adds another layer of complexity. LIGO and Virgo have detected dozens of black hole mergers with masses ranging from 7 to 90 solar masses. The distribution suggests that massive black holes like Gaia BH3 are common throughout the universe. But gravitational wave detections come with their own biases. The technique favors equal mass binaries in tight orbits that spiral together rapidly. Single black holes and wide binaries like Gaia BH3 remain invisible to current gravitational wave observatories. The upcoming LISA mission, scheduled for launch in the mid-2030s, will extend gravitational wave astronomy to lower frequencies. This space-based detector array should identify compact object binaries throughout the Milky Way, providing an independent census of the black hole population. Early estimates suggest that LISA will detect dozens of stellar mass black hole binaries within our galaxy. Combined with Gaia's astrometric discoveries, these observations will finally reveal the true extent of the hidden population that surrounds us. The formation mechanisms underlying this population challenge conventional stellar evolution models. Traditional theories predict that stars more massive than 25 solar masses undergo parent stability supernovas that completely destroy them, leaving no black hole remnant. Yet LIGO has detected black holes with masses exceeding 50 solar masses. Gaia BH3's 33 solar mass falls within the theoretical mass gap, where conventional models struggle to explain black hole formation. Its existence, along with similar discoveries from gravitational wave astronomy, forces revision of stellar evolution theory. The metal-poor environment that likely gave birth to Gaia BH3 provides crucial clues. Stars with low metallicity experience weaker stellar winds, retaining more mass throughout their lives. This retention allows them to collapse into more massive black holes when their nuclear fuel is exhausted. If this formation channel dominated in the early universe, when heavy elements were rare, it suggests that massive black holes should be more common in old stellar populations. The galactic halo, composed primarily of ancient metal-poor stars, may harbor a disproportionate number of these invisible giants. This demographic distribution has implications for encounter rates with our solar system. The Sun's orbit through the galaxy periodically carries it through different stellar populations, including occasional passages through the metal-poor halo. These excursions may increase the probability of close encounters with massive black holes. Recent analysis of stellar streams and galactic dynamics suggests that our solar system has experienced several close encounters with dense stellar clusters throughout its history. Some of these interactions may have involved black holes massive enough to perturb planetary orbits or disrupt the outer solar system. The geological record preserves evidence of ancient catastrophes that may correlate with such encounters. Mass extinction events, climate disruptions, and changes in cratering rates could reflect gravitational disturbances from passing massive objects. While these connections remain speculative, they highlight the importance of understanding the true black hole population. If invisible giants wander through our galactic neighborhood more frequently than previously thought, their gravitational influence may have shaped Earth's history in ways we're only beginning to recognize. The space agency response to these discoveries reflects careful balancing of scientific transparency with public perception management. Press releases emphasize the excitement of discovery while downplaying potential safety implications. Technical papers bury population estimates in statistical appendices that few outside the field will read. This communication strategy extends to international space policy. The United Nations Office for Outer Space Affairs maintains guidelines for reporting potentially hazardous objects, but these protocols focus on near-Earth asteroids and comets. No equivalent framework exists for assessing or communicating black hole encounter risks. The absence of formal threat assessment protocols reflects both the perceived remoteness of black hole encounters and the limited detection capabilities that have historically made such assessments impossible. But as observational astronomy reveals a more populous and dynamic black hole environment, these policy gaps may require attention. Meanwhile, the astronomical community grapples with the implications of living in a galaxy far more densely populated with massive objects than previously imagined. Each new discovery forces revision of models that have guided space exploration planning and planetary defense strategies for decades. The hidden population that Gaia BH3 represents isn't just an academic curiosity. It's evidence that our cosmic neighborhood contains invisible giants whose gravitational influence may extend far beyond current detection limits. As we prepare to examine the classified dimensions of black hole research, one thing becomes clear. We're not alone in the galaxy, and our companions may be more numerous and threatening than we ever suspected. The reality of living in a galaxy populated by millions of invisible giants forces a fundamental recalculation of cosmic risk. While space agencies maintain that no black hole poses immediate danger to Earth, the discovery of massive objects like Gaia BH3 in our cosmic neighborhood challenges the assumptions underlying those reassurances. Current NASA safety assessments focus on the gravitational stability of known black holes in wide binary systems. These calculations demonstrate that even if our Sun were replaced by a black hole of identical mass, Earth would continue its orbital path unchanged. The gravitational effects would remain the same, though obviously the absence of sunlight would prove problematic. But this analysis assumes static conditions that may not reflect the dynamic reality of galactic evolution. Computer simulations of stellar dynamics show that gravitational interactions can alter orbital paths over millions of years. Close encounters with massive objects, including black holes, can perturb planetary systems in ways that unfold gradually over geological timescales. The discovery of hypervelocity stars ejected from our galaxy provides direct evidence of such violent interactions. These stellar refugees, traveling at speeds exceeding millions of miles per hour, were likely accelerated by close encounters with supermassive black holes. Their existence demonstrates that gravitational slingshot effects can dramatically alter the trajectories of astronomical objects. Recent analysis of hypervelocity star populations has revealed an unexpected pattern. Roughly half of these stellar refugees appear to originate from Sagittarius A*, the supermassive black hole at our galaxy's center. But the other half show trajectories consistent with ejection from a previously unknown supermassive black hole in the Large Magellanic Cloud. This finding implies that our local galactic environment contains more massive gravitational sources than previously recognized. The presence of a supermassive black hole in our largest satellite galaxy adds another dynamic element to the already complex gravitational landscape surrounding our solar system. The implications extend beyond individual encounters to the cumulative effects of multiple gravitational perturbations. Mathematical models of galactic dynamics suggest that planetary systems experience thousands of close stellar encounters over their lifetimes. If a significant fraction of these involve black holes, the cumulative perturbations could gradually destabilize planetary orbits. These concerns gain urgency from paleontological evidence of periodic mass extinctions throughout Earth's history. Some researchers have proposed correlations between extinction events and our solar system's oscillations through the galactic plane, where encounters with dense stellar populations and massive objects become more likely. While these connections remain speculative, they illustrate how black hole encounters might influence Earth's environment indirectly. Gravitational perturbations could disrupt the Oort cloud, sending comets toward the inner solar system. They might alter Earth's orbital eccentricity, affecting climate stability over geological timescales. The classified dimensions of black hole research extend beyond academic speculation into national security considerations. Government space agencies maintain detailed threat assessment models that incorporate more sophisticated analyses than those released to the public. These classified evaluations consider scenarios that might cause panic if widely discussed. Freedom of Information Act requests have revealed limited glimpses into these classified assessments. NASA's Planetary Defense Coordination Office maintains contingency plans for various astronomical threats, including protocols for responding to unexpected gravitational anomalies. The specific details remain redacted, but the existence of such plans confirms official recognition of potential black hole risks. The European Space Agency's approach to threat communication reflects similar concerns about public perception. Press releases about Gaia BH3 emphasized scientific excitement while avoiding detailed discussion of population statistics or encounter probabilities. Technical papers bury risk assessments in mathematical appendices that few outside the scientific community will examine. This pattern of selective disclosure extends to international space policy. The Committee on the Peaceful Uses of Outer Space maintains guidelines for sharing information about potentially hazardous objects, but these protocols were developed primarily for near-Earth asteroids. No equivalent framework exists for coordinating black hole threat assessments or response strategies. The absence of public protocols reflects both the perceived remoteness of black hole encounters and the recognition that such discussions could generate counterproductive anxiety. Space agencies walk a careful line between scientific transparency and responsible risk communication. Yet, the discovery pattern emerging from Gaia's survey suggests that this balance may require recalibration. If massive black holes exist in numbers that significantly exceed previous estimates, the cumulative encounter probability over geological timescales might warrant more systematic evaluation. The gravitational wave astronomy perspective adds another layer of complexity to threat assessment. LIGO and Virgo detections reveal that black hole mergers occur throughout the universe at rates higher than initially predicted. These mergers release gravitational waves that carry energy equivalent to several solar masses converted entirely to radiation. While gravitational waves from distant mergers pose no direct threat to Earth, they provide insights into black hole population dynamics that inform local risk models. The frequency of detected mergers suggests that black hole interactions are more common than previously thought, implying higher encounter rates in all galactic environments. The upcoming LISA mission will extend gravitational wave observations to lower frequencies, potentially detecting black hole binaries throughout our galaxy. This capability will provide the first comprehensive census of compact object pairs in our cosmic neighborhood, revealing systems that might eventually interact with our solar system. Early simulations suggest that LISA will detect dozens of stellar mass black hole binaries within a few thousand light-years of Earth. Some of these systems may be gravitationally bound to our solar system's motion through the galaxy, creating the possibility of eventual close encounters as orbital dynamics evolve over millions of years. The formation mechanisms that created Gaia BH3 and similar massive black holes also influence their subsequent behavior. Objects formed from metal-poor stars in the early universe likely received different natal kicks from their supernova explosions compared to more recent black hole formation events. These kick velocities determine whether newly formed black holes remain gravitationally bound to their birth locations or escape to wander through the galaxy as isolated objects. Recent theoretical work suggests that the most massive black holes, like Gaia BH3, may receive relatively small kicks, keeping them in stable galactic orbits. This orbital stability has contradictory implications for solar system safety. On one hand, stable orbits make black hole trajectories more predictable, allowing better long-term risk assessment. On the other hand, stable populations increase the probability that our solar system will eventually encounter one of these invisible giants during its galactic journey. The timescales involved in these processes span millions to billions of years, far beyond human civilization's current planning horizons. Yet, the discovery of Gaia BH3 forces recognition that our cosmic environment contains more massive gravitational sources than previously understood. This recognition has practical implications for space exploration planning. Current proposals for interstellar missions assume relatively benign gravitational conditions in our local galactic neighborhood. But if massive black holes populate this region more densely than expected, mission planners may need to account for gravitational hazards that could affect spacecraft trajectories. The Pioneer and Voyager missions, now in interstellar space, provide early tests of these assumptions. Anomalous trajectory deviations detected in these spacecraft have generated speculation about unknown gravitational sources, though conventional explanations involving thermal effects appear more likely. Future interstellar missions will carry more sophisticated instruments capable of detecting gravitational anomalies that might indicate the presence of nearby black holes. These observations will provide ground truth for models of local space conditions that currently rely heavily on theoretical predictions. The broader implications of living with invisible giants extend beyond immediate safety concerns to fundamental questions about humanity's place in the cosmos. The discovery that our galaxy contains millions of objects massive enough to disrupt planetary systems challenges anthropocentric assumptions about cosmic habitability. If black holes significantly outnumber visible stars in some regions of the galaxy, they may play a dominant role in shaping the gravitational environment that determines where stable planetary systems can exist. This influence could help explain why complex life appears to be rare in the universe, despite the abundance of potentially habitable worlds. Conversely, the same gravitational interactions that pose long-term threats might also provide benefits. Black hole encounters could trigger periods of intense comet bombardment that deliver water and organic compounds to developing worlds. They might induce orbital changes that improve climate stability on planets trapped in snowball states. These competing effects illustrate the complexity of assessing black hole influence on planetary habitability. Rather than simple threats or benefits, invisible giants may be essential components of galactic ecosystems that determine where and when complex life can emerge. The philosophical implications extend to humanity's long-term survival strategies. If our solar system exists in a gravitational environment dominated by invisible massive objects, this reality must inform decisions about space colonization, resource allocation, and species preservation. Some researchers advocate for accelerated development of space-based civilization as insurance against astronomical catastrophes. The discovery of Gaia BH3 and the hidden population it represents adds weight to arguments for establishing self-sufficient colonies beyond Earth's gravitational well. Yet the same black holes that threaten Earth-based civilization might also endanger space-based habitats. Artificial habitats in deep space would be even more vulnerable to gravitational perturbations that could alter their trajectories or disrupt their structural integrity. The ultimate message emerging from Gaia BH3's discovery is one of cosmic humility. Our galaxy contains invisible giants whose gravitational influence extends across vast distances and geological timescales. Understanding their distribution, behavior, and potential impacts represents one of the most important challenges facing modern astronomy. As space agencies continue their careful balancing act between scientific transparency and public reassurance, the hidden population of black holes revealed by missions like Gaia forces a more nuanced understanding of cosmic risk. We live in a universe far more dynamic and potentially threatening than previous generations imagined. Yet this knowledge also empowers us to prepare for challenges that our ancestors could never have anticipated. By mapping the invisible giants that populate our cosmic neighborhood, we take the first steps toward true cosmic situational awareness. The monsters may be closer than we thought, but for the first time in human history, we're learning to see them coming.